Hello and welcome to episode 27 of Samsplaining Science. I'm Sam, I'm your host. I'll be Samsplaining the science, and today we're talking about statistics. Don't leave. It'll be fun, I promise. Well, maybe not fun. Fun is a strong word, but it'll be okay, I promise. Let's get into it. Hi everyone, how are ya? I hope you're doing well. I'm doing fine. It's been a while. I've missed ya. Some of you may have been concerned that I dropped off the face of the earth. That's actually not what happened, thankfully. But no, if you're following on Instagram, which if you're not, follow at SamSplainingSci. But if you're following on Instagram, you may have seen that I announced a little bit of a hiatus and explanation for why I haven't posted a podcast in a couple weeks, a month. But I was a little busy in preparing for and then attending a research conference. While I was at the conference, I made TikTok/Reels each day, sort of documenting my experience back at a conference. So if you haven't seen those, you can check them out on my Instagram at SamSplainingsci, and then also on TikTok at SamSplainingscience if you want to follow there. But yeah, that was really fun. It was, excuse me, it was a very good experience. It was nice to be back at a conference, but it was also very just like a lot going on. But making the TikToks was fun to like document my day and like sort of show that side of sciencing, because sometimes that's like one of the more fun sides of doing science. So I'm glad I got to share it. But yeah, now I'm back from the conference and just trying to get back to a normal workflow in terms of the podcast, at least. I know it's been over a month since I've posted an episode, and I'm very sorry, but I'm excited to get back to the normal posting schedule, which the day changes each week, but once a week you'll get an episode, I promise. Yeah, but this is my third time trying to record this episode. The first time my computer like shut down. I was almost finished recording the episode, and then my computer shut down and I lost everything. So that was a really nice welcome back to podcasting after a month hiatus. It was like, you thought this was going to be easy? No, it was not. So that was lovely. And then the second time I was recording it, I just didn't feel like it was going that well. I just wasn't like, I don't know. I was like, this is sort of awful. So I just stopped recording mid-episode, and I was like, I'll try again later. And now this is later, time number 3. So hopefully third time is a charm, and this take goes well. Because if it doesn't go well, then I'm just going to post a bad episode, because I just need to get on with it. Why is my voice so, what's wrong? You know what it is? It's because I've recorded this episode 3 times in the span of like 24 hours. That's why. Okay. Okay. So as I mentioned, today we're talking about statistics. We're doing a little stats crash course. The title of the episode is Let's Talk About Stats, Baby. Like that song, but they're not talking about stats in the song. They're talking about something else. But yeah, so we're going to talk about stats. We're going to basically understand, hopefully by the end of the episode, we'll understand like what we do with data, whatever that means, and how we, after we collect it, how we analyze it and turn it into meaningful observations and conclusions. So that's the overarching goal for this week's episode. So let's get into today's questions. We have 3 questions today. The first one is, what data can we collect? This is really just like a background about like the types of data that scientists can collect. The next question is, how can we use statistics to describe a sample population? And then the third question is, how can we use statistics to test a hypothesis? And as always, sources that were used in making this episode are in the description of the episode. So please check them out. Okay, so first question, what data can we collect? A lot of this episode is going to be just like definitions, but hopefully as I go through the definitions, I'll like have examples or like run through the definitions and then provide an example after. But just sorry if I sound like a robot. But I'm going to try not to sound like a robot, but if I do, sorry. So the definition of statistics is the collection, analysis, and interpretation of numerical data. We, as scientists, can collect data in a couple of different ways, in a couple of different contexts, right? If we're looking at things like temperature or blood pressure, or if we're taking a survey and we ask people to rank or like put their mood on a scale of like 1 to 5, anxiety levels on a scale of 1 to 5. Those are all like types of data that we can collect. And then we collect that data and we analyze it. So the two different types of data we can classify in two different ways. The first is categorical data and the second is continuous data. So categorical data, as the name suggests, is basically like the data are divided into categories. This could be like a binarized data, like a yes or no, or a 0 or a 1 answer. They could also be categories like blood type, like collecting information about a person's blood type, whether they're A, B, or O. It also includes survey data. So like I mentioned, like the anxiety scales from 0 to, or like from 1 to 5. Or like if you've ever taken a personality test or like any of those tests where it's like, they say a statement and then they're like, do you strongly agree with this statement or moderately agree with this statement or neither agree nor disagree? Basically, any data, any question that we're collecting answers for, where the answers are in a category, where they're sort of already defined, predefined, and there's not really much flexibility in terms of like, if you rate it from 1 to 5, it has to be either 1, 2, 3, 4, or 5, right? Like most people, most normal people who say like, oh, on a scale of 1 to 5, I'm going to give it like a 1.266. It's like, just say 1, you know? That's categorical data, is having predefined, solid set categories and collecting responses within those categories. The second type of data is called continuous data, and this is the data that's more flexible. It's more, you're able to measure something with more precision. And what I mean by that is like it has a decimal point. So for example, a distance, 2.561 meters, times of, 8.22 minutes, whatever. Things that have precision with a decimal point are considered continuous data. And that's different from categorical data, which is less flexible. It's more rigid, of either yes or no, 1, 2, 3, 4, 5. So hopefully that ramble that I just did helped to clarify the difference between categorical and continuous data. One other thing that I want to talk about before we get into the next question is about population versus sample. So when we're thinking about a population is the entire group. So like if we're talking about, like I do Alzheimer's research, right? So the population that I'm studying is patients who've been diagnosed with Alzheimer's disease. But the studies that I do are not on the full population, right? I'm not taking pictures of every single Alzheimer's patient's brain, right? I'm taking a sample, a subset of the population, and looking at their brains. And then from that sample, drawing conclusions based on, or like expanding the conclusions from that sample to the population. The same thing goes for like when there are political polls, right? When there are political polls that are like, what issues do you care about? The sample, they're not calling up every single registered voter in the US and asking what issues they care about. They're calling a select subset sample of the registered voter population in the US and gathering that data from the sample. And then from that, they're extrapolating to the whole population. It would be nice to measure in the entire population all of this data. It would be nice to get, biological data from every single patient in the world. But it's just not practical, right? It's not going to happen. So we collect data in a sample and then expand that understanding from the sample to the population. Okay. One thing I want to note also, on top of the thing that I'm noting right now about the population versus the sample, is beware of the biased sample. So if I were to say, ask 10 people, what is your favorite color? Red, orange, yellow, green, blue, purple. Of those, what is your favorite color? Categorical data. And of the 10 people, 4 of them say green, and then the remaining 6 are sort of spread out. Then I could say, okay, well, 40%, 4 out of 10, 40% of the sample had green as their favorite color. So if we're going to draw a conclusion of the population based on the sample, we could say about 40% of the population has green as their favorite color. But that's if the sample that I took was representative of the population. It would be an issue and it would be biased if I stood outside of like, a store that like only sold blue things. And I like asked people coming out of the store, hey, what's your favorite color? And they go, my favorite color is blue. And all 10 people that I ask walking out of the blue store, their favorite color is blue, right? So the conclusion that I would draw from that sample is that 100% of people have blue as their favorite color. And that sample is biased because of where I collected it. And it's not representative of the whole population. So that's just something to be mindful of when you're collecting data, is be careful of the bias. Okay, hopefully that's sort of like a clear summary of what kind of data we can collect and like some considerations that we should keep in mind when we're collecting data within a sample. So that's question 1. Moving on to question 2, we're going to ask, how can we use statistics to describe a sample/population? So I'm going to run through these definitions, sort of like explaining them, like the raw definition of these key concepts, and then I'm going to do an example afterward that sort of shows how each of these concepts can be used to describe a data set within a sample. So the first key concept I want to talk about is the sample size, also known as N. N is the number of data points in the sample. It tells us the size of the sample. You're welcome. Honestly, thank God I'm here. I'm sure you would be totally lost without me. But yeah, no, sample size just gives us an idea about how many people are in the sample or how many data points are in the sample. And then from that, we can understand how, how much we can trust the data. And we'll get into this a little bit more later if we have time. But basically, the more people we sample, the more representative we are of the population as a whole. So like if I ask 3 people what their favorite color is versus asking 300 people, then I would have a much better idea of the population if I ask 300 people versus 3. So that's sample size. The next key concept I want to talk about is the average. There's a couple of different names for this. There's average, there's sample mean, there's mu, which is a Greek letter, mu. But basically, the average of the data set tells us the value which we expect to see in the population. It gives us a ballpark idea of what this measure should be in the population. And the way that we calculate it is by taking every individual's measure, every individual's response, adding them up and dividing them by the sample size or the number of measures, right? So if we asked 10 people their age, we'd add up all the ages and divide by 10 to find the average age. So that's average, also known as sample mean, also known as mu, also known as expected value. Sometimes they just make it more difficult for no reason. But that's none of my business. The next key concept we're going to talk about is range. And the range here means the minimum and maximum data values. So it basically gives a limit to the possible measurements, responses. So if we're sticking with asking 10 people their ages, let's say the youngest person that we ask is 18 and the oldest person that we ask is 45. Then the range of our data set is 18 to 45. So we know that, all of the data points that we've collected will be between those two numbers. Oh, man. I'm sitting on the floor. I was like, oh, that might be comfortable. It's not. Spoiler alert, it's not. Okay. So that's range. The next key concept is the median. Honestly, this might be stuff that you're like, oh yeah, I remember learning this in 4th grade. Because that's when I remember learning it. Maybe not 4th grade. Maybe I don't know, honestly. I don't have a memory. It's gone. The median is the middle value if we were to order all of the measurements in ascending order. So let's say the range maximum, we're going to stick with that range of 18 to 45, right? So starting with 18, we would start with the lowest ages and then work our way up. And then the last number in the list would be 45, which is the maximum. And we would list the ages of the 10 people that we asked in ascending order and then find the value that's in the middle. Because the list isn't even number, it has 10, we would take the average of the two middle values to get the median. But basically this just tells us where the middle of the pack is. What the middle value is, where the middle of the range is, because it might not be right in the middle of 18 and 45, right? Let's just say there was only one person that we asked that was 45 years old, and then after 45, the next oldest was 30. In that case, the middle of the pack isn't going to be right in the middle of 18 and 45. It could be 22, 24, depending on what the data looks like, right? So the median just tells us where the middle is. The next key concept is the mode. The mode is the most frequently observed data value. It's the data value that shows up the most often. So in our group of 10, we have an 18-year-old, a 45-year-old, and maybe we have 5 30-year-olds. So 30 would be the mode, because that's the most frequent age in our sample. The next key concept, I kind of combine these two together because they're kind of related. They are related to one another. The standard deviation and the variance. These two are often shown, represented, I don't know what the right word is, depicted as the Greek letter sigma, the lowercase sigma, where standard deviation is equal to sigma and variance is equal to sigma squared, or sigma to the second power. Both of these concepts tell us about the variability, or like the spread of the data from the average, from the sample mean. But they're calculated because they're different. One is sigma and one is sigma squared. They're calculated in different ways. So the variance is equal to the distance of each data point to the mean squared divided by the sample size minus 1. So let's just say in our sample the average was 30. We would take every sample, 30 minus 18, 45 minus 30, and we would measure the distance of each data point to the mean, and then square that value, multiply it by itself, and then divide that by the sample size, which is 10 minus 1, so divided by 9. That's how we find the variance. And then the standard deviation is the square root of the variance. And one reason why I'm sort of harping on one is squared and the other is not squared is because this affects the units of the measurement of standard deviation versus variance. So because the variance has the measurement squared, so like observed data point minus average squared, that means that like 45 years old minus 30 years old squared is 15 squared. I don't know what that is. I should have chosen a better number. But 15 years squared, right? 15 times 15 years squared is let me Google this quick. Look at me. I'm like, oh, I'm an engineer. I love numbers. And then I can't do math in my head. 225. I could have been able to do that if I sat and thought about it, but I didn't want to think about it, okay? So then it would be 15 years squared equals 225, and then the unit of that 225 is years squared. What is a year squared? I don't know. I don't think it means anything to me, and I don't think it means anything to you either, right? But when we take the square root of that, we finish the calculation of variance, and we do 225 divided by 9. I'm not even going to calculate that. I don't care about it. The point is that if we finish that variance calculation and then we take the square root of it to find the standard deviation, that unit is in years, which is something that I can understand, right? I know what a year is. I don't know what a year squared is, but I know what a year is. So the standard deviation puts this idea of the variability of the data into a unit, into a context that makes sense with respect to the data that we're collecting. That's the whole point of this spiel. And then I guess just one more thing before I move on to the next concept is, I keep saying that a lot. One more thing. It's like 1,000 more things at this point. Just say what you want to say, Sam. Anyway, when thinking about the standard deviation, the smaller the number of, the smaller the value of the standard deviation means that the data are all closer to the mean. There's less distance between each data point and the mean when the standard deviation is low compared to if the standard deviation is larger. That means that the data are further away from the mean. And why do we care about this? We care about this because it helps us understand the distribution of the data, which is the next key concept, is the distribution. So we can look at the distribution, we can actually visualize the distribution of the data as a histogram, where basically we bin the data into intervals, right? So we'll set intervals as like 18 to 23 years, 24 to 29 years, 30 to 34 years, and then we'll count up all of the people who fall within those intervals, within those ranges, to get the frequency. And then we'll have a bar plot where the x-axis will be the age intervals. So like one bar will be representative of 18 to 23, one will be 24 to 29, and so on. And then the height of those bars will correspond to the frequency with which we see that age range in our sample. So like the age ranges that have more people will have taller bars. So that's sort of like how we can visualize a distribution with a histogram. So let's talk about an example, one type of distribution, which is called a normal distribution or a Gaussian distribution, if you're feeling fancy, but otherwise a normal distribution. Most data, I don't want to say all data, but most data follow this idea of a normal distribution. So let's talk about it. So if you're watching on YouTube, which by the way, if you're not, go to YouTube and search Samsplaining Science and you can watch this episode. I pulled a figure from Khan Academy. Shout out Khan Academy. They got me through all of my college math courses. But they provide this very nice figure that I honestly couldn't replicate if I tried, of a standard normal distribution. So the figure here shows what is a normal distribution, which is basically it's shaped like a bell curve, and it's a frequency plot, a histogram of sorts, like I mentioned before, where the x-axis is bins of data values, and the y-axis is the frequency with which we observe the data in these intervals, right? So the shape of the normal distribution is a bell curve. It looks like a hill, right, where there's a low frequency at the beginning. It starts like very close to zero, and then a high frequency in the middle, where it peaks like the top of the hill, and then it comes back down on the other side, close to zero at the end. So it's like symmetrical on both sides with a peak in the middle. The distance along, I think I kind of said that already, but basically the distance in the x direction along the curve tells us the data value, and then the height tells us how frequently we observe that value in our data set. So when the data that are collected are normally distributed, as shown here, the peak of the hill, so the top of the hill, is three things simultaneously in like a perfectly normal distribution. The peak of the hill is the mode. It's observed the most often, and that makes sense, right? Because if we're looking at the value of the distribution curve as the frequency, the most frequently observed data point will be the highest bar. So it's the mode. It's also the median, meaning that it's in the middle of the distribution and that it's symmetric on both sides. And it's also the mean, or the average value of the data set. So in a perfect normal distribution, most of the data are centered around this peak in the normal distribution that should be equal to or very close to the mode, the median, and the mean. So in the example figure that's shown here, the mean is 0. This is called a standard normal distribution, where the mean is 0 and the standard deviation is equal to 1. So in this case, the distribution curve starts a little below -3, and then it peaks at 0, and then it goes back down and goes to 0 a little bit after positive 3. So it's centered around 0, and then from -1 to +1 is 1 standard deviation on either side of the mean. -2 to +2 is 2 standard deviations on either side of the mean, and so on. If the standard deviation was less than 1, this peak, this hill, would be a lot steeper and like closer together. If the standard deviation was greater than 1, the peak would be shorter and flatter and more spread out. So remember how I mentioned like the standard deviation tells us about the spread of the data, right? So if the data is more spread out, it's going to have a higher standard deviation. Okay. Still thinking about, so now we can see that we can characterize this normal distribution based on the mean and the standard deviation. But one more concept that I'm going to talk about before we can get into like the example that I made up is this idea that the standard deviations past the mean reflect the density of, or the distribution of the data set, right? So like on this figure here, it shows that within 1 standard deviation of the mean, almost 68% of the data are within 1 standard deviation of the mean. So like most of the data fall within 1 standard deviation of the mean. And if we go out to 2 standard deviations past the mean, that number jumps to 95%. 95% of the data that we collected fall within 2 standard deviations of the mean. And if we go out to 3 standard deviations, that number jumps up to 99.7. So almost 100% of the data that we observe in a normal distribution fall within 3 standard deviations of the mean. So if we think about this sort of as like a probability, what is the probability that we see this measure in this data set? When we look at this normal distribution curve, within 2 standard deviations, we can say with confidence that there's a 95% chance, 95% probability that a data point on average lies within, -2 standard deviations and +2 standard deviations of the mean, right? And it's far less common, far less likely, far less probable for a data point to be outside of these bounds, right? So we can call this range of like the mean plus or minus 2 standard deviations a 95% confidence interval, meaning that 95% of the time the data will be in this range. Okay. So this is hopefully giving some insight as to, okay, we can calculate the mean, we can calculate the standard deviation, but now we can use the mean and the standard deviation to describe and characterize what the distribution of the data look like. And we can characterize what shape the distribution is, and then from there, understanding how we can use the mean and the standard deviation to describe the data that we're collecting. Okay, so that was all the concepts that I wanted to talk about for question 2, but first, before we move on to question 3, I want to do an example, okay? So this is an example that I made up. I asked, in quotes, 17 people, how many vegetables did you eat today? Okay, so here's my sample. I'm going to read it off, even though this will probably mean nothing for the audio people, but so my sample of 17 answers to how many vegetables did you eat today are 6, 3, 4, 3, 3, 2, 1, 2, 4, 4, 5, 1, 2, 3, 0, 3, 5. And what we're not going to do is judge the person who said 0, because there's been more than one time in my life where I have laid my head down on a pillow at night and said, did I eat a vegetable today? And it happens, okay? And we're not going to judge it. It doesn't happen every day, and it shouldn't happen every day. Eat your vegetables. But what we're not going to do is judge people who forget to eat a vegetable in a day, okay? Let's talk about the number 6. Do less, buddy. Relax with you're going to OD on vitamin A. All right, anyway. The first thing that we're going to do once we get the sample is just order it from minimum to maximum, right? So now we have the same list, the same data, except in ascending order. So it's 0, 1, 1, 2, 2, 2, blah, 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 all the way up to 6. So as I mentioned, I asked 17 people how many vegetables they ate in a day. So my sample size is 17 because I received 17 responses. I received I don't know if you heard that, something just crashed. I received 17 responses, so my sample size is 17. I can take the average or the sample mean or the mu of my data set by adding up every single response and then dividing it by the sample size. So when I do that, I get 3 vegetables is the average. I can also take the median by finding the middle value in the ordered sample. So here we have the 17 samples lined from least to greatest. And if we find the ninth data point with 8 on either side, that is the median. That's the middle of the pack, which happens to be 3 vegetables. Lastly, we're going to look at the mode, and it's also looking at the ordered sample. We can see that there were 3 people who said that they ate 2 vegetables in the day. There were 5 people who ate 3 vegetables, 3 people who ate 4, 2 people who ate 5. So we'll say that the mode is 3 vegetables because that's the most frequent response that we got in our data sample. Then we calculate the sigma and the sigma squared, which are the standard deviation and the variance respectively. And we find that the standard deviation is 1.633 vegetables and the variance is 2.667 vegetables squared. What is a vegetable squared? Diced. That was really funny, and I just thought of that off the top of my head. Honestly, wow. Get it? Like a diced vegetable? Bye. Okay. Lastly is the distribution or the histogram of the data. So I'll describe it with my words in case you're just listening. But basically, it's a normal distribution where the mean, the median, and the mode are all equal to 3. So the peak of the bell curve is at 3. And then as we move away from the mean, we see less and less frequency as we get out to 0 and 6, which each have 1 response each. So it looks like a very perfectly normal distribution. It's almost like I made it up. Crazy. There are other types of distributions besides the normal distribution that I want to give shout out to. The first one is a uniform distribution, and this is when the frequency of the data points, the data responses, are all the same. So if I were to ask, how many vegetables did you eat today? And the same number of people who answered 0 also answered 1, also answered 2, also answered 6, so that every single number, every single category had the same frequency, and there was just like a straight line across the distribution. That's a uniform distribution. Another type of distribution is called a bimodal distribution. This is when there are 2 different modes in the data. So in this case, if we were to consider, again, 0 to 6 vegetables, it would be like if the same number of people answered 2 and 4, and that frequency was higher than 3. So there would be sort of like multiple peaks in the distribution, which indicate multiple modes in the data. That's bimodal. Another type of distribution is a skewed distribution. This is sort of like a normal distribution. It has one peak, but it's not symmetrical. So one tail is longer, like more extended than the other because the peak is skewed closer to one end of the range. It's not right in the middle, so it wouldn't be 3 vegetables, it would be 1 vegetable is the most frequently observed. It's the peak of the distribution, and then the rest of the tail of the curve sort of skews until it gets to 6. But as I mentioned, most measurements in science and nature conform to this sort of normal Gaussian distribution. Like, think about people's heights, right? Some people are on the shorter side, some people are on the taller side, but most people kind of fall within the average height. So that's sort of a way to think about the normal distribution. Most people are average. So hopefully with this question, we have a better understanding of how we can characterize or like summarize the data and visualize the data distribution based off of how the data looks, using things like the mean, the mode, the median, the standard deviation, etc. Okay, so that's question 2. Now we'll move on to question 3, which is where I stopped the last time that I recorded because I was like, I'm just not feeling this. I don't think I was doing a good job of explaining things, so we'll see if I've improved since this morning. Probably not. But we'll try. All right. Hopefully this turns out better. Okay, question 3. How can we use statistics to test a hypothesis? So first I want to give a shout out. I keep saying that today. Shout out. I want to cite the source that I used to remind myself, refresh my memory, gather my thoughts. But it has a lot of useful information about hypothesis testing in a lot more detail than what I'm going to cover. So that is one that is linked in the episode description. But it's by Drs. Emmert Streeb and Dr. Damer. And it's Understanding Statistical Hypothesis Testing, published in 2019. So thanks for helping me refresh my memory about what we're going to talk about. All right, so now let's throw it back to the scientific method that we learned in like 2nd grade, when we know that the scientific method it starts with a question, right? And then from a question, you form a hypothesis on what you think the answer to that question is. And then you base that hypothesis on things that you already know, and you make like an educated guess, right? Then you collect data and analyze that data, and then from that analysis you can draw a conclusion. You can make a conclusion. And it's the statistical analysis of that data that we collect that helps us answer our question with more confidence, with more certainty. And depending on the type of question that we ask and the type of data we collect, based on our experimental design, we can do different types of statistical analyses. And these statistical analyses will tell us the probability of us measuring what we're measuring, and if it's measured by chance or if it's real. So the question and the hypothesis steps of the scientific method will help us decide what kind of statistics we should use. So I listed a couple of examples here. Like if we want to see if 2 or more measures are associated with one another, we can do a regression analysis or a correlation analysis. If we want to see if a certain condition or an intervention has a significant difference or effect from a control condition or from baseline, we can use a ttest or an ANOVA. And I'm not going to go through all of these today. Today I'm just going to be focusing on the t-test, but this is just to say that for most questions in science, there is a statistical test that will tell us how reliable and how trustworthy our findings are based on the data that we collected. So that's how we use statistics for hypothesis testing. So I want to come back to this idea of the hypothesis for a minute. As I said, I'm talking today mostly about the t-test, which we'll get into in a second. But this idea of a hypothesis in science, from when I was a kid, I remember learning about like making a hypothesis and being like, I predict that this will happen. And that is essentially what a hypothesis is, but it's a little more than that as well. So in science, we have what's called the null hypothesis, which is also known as H naught. And the null hypothesis is basically, if we're thinking about in terms, if we want to compare two groups. An example, like when I was a kid, I would say, I think group 1 is greater than group 2. But in practicing science, we don't have that exact hypothesis. We have what's called a null hypothesis and an alternative hypothesis, where the null hypothesis is that there is no difference between group 1 and group 2, right? So it's null. The difference between the two groups that we're looking at is null. It does not exist. There is no difference. They are the same. The alternative hypothesis is the traditional hypothesis that we think of when we say there is a difference between the group. I think these two groups are not equal to one another. One might be greater, one might be less, or we could just say they're not equal to each other. I think that they are different. There is a difference between group 1 and group 2. That's the alternative hypothesis. Usually, as I said, that's like the traditional hypothesis, and we want that to be true, right? Usually we're saying like, okay, if we're testing a drug, for example, we want the group that gets a drug to perform better on a cognitive test than a group that doesn't get the drug. But in order to accept that hypothesis and say there is a difference in performance between the drug group and the no drug group, we need to prove that the null hypothesis is not true. So we need to prove that there isn't no difference between the groups. Do you hate statistics yet? Be honest. It's a little bit like the logic is a little wonky, but basically we need to reject the null hypothesis in order to accept the alternative hypothesis. We need to reject the idea that there's no difference in order to accept the idea that there is a difference. And how do we do that? With probability and statistics. So now we're going to get into the t-test. The whole point of the t-test is to explore if there's a difference between sample means, either within a group before or after an intervention, or between groups, like between patients or controls, or between treated versus untreated participants. So the t-test assumes that the data are normally distributed, so they follow that bell curve, and they take into account a couple of key values, a couple of key variables. So one of these is the significance level called the Greek letter alpha. So alpha represents the type 1 error, which is the probability of a false positive. So I feel like maybe now people have a better idea of like what a false positive and a false negative is when with regard to like COVID testing. But basically a false positive is when you get a result that says yes, but the real answer, the actual answer is no. So it's false positive. A false negative is when you get an answer that is no, but the answer is actually yes. But the type 1 error, which we're talking about when we think about alpha, is the probability of a false positive, meaning that it's the probability that we're going to get a yes when the answer is no. And we typically set this value at 0.05, or also known as 5%. In other words, we accept that there is a 5% chance that we are going to see a false positive in our data. That is the acceptable value that we put. And it's sort of like a value that's hard-coded. Like most studies, most scientists implement this alpha equals 0.05. There are some exceptions, but for the most part, alpha is pretty consistently 0.05. And with this idea that like we'll accept a 5% chance that our results are a false positive, anything less than 5% chance, so if our data tells us that there's actually less than a 5% chance of a false positive, amazing, awesome. We're going to trust our data because it's less likely that our yes answer is false. But if our data suggest that there's a greater than a 5% chance of a false positive, then we feel less confident in our results and less confident in our data, and we say that they're not significant. So less than 5%, we say, this is significant, this is real data. Greater than 5%, we're less confident, and we say these data are not significant. But how do we find out what our probability from our data of a false positive is? For a t-test, we have to calculate what's called the t-statistic. And it uses this complicated formula that I'm not going to walk through, but one thing I want to call attention to is that it is related, this t-statistic is related to the difference between the two sample means, so the sample mean in group 1 and the sample mean in group 2. And it's also related to the variances, so the sigma squareds, and the sample sizes for each group. So each time you do a data collection, each time you do an experiment, this t-statistic will change. And it depends on the sample mean or the mu of each group, the sample size, and the variance of each group. But once we can calculate this t-statistic, we can move on to the next step. The next step is a little more complicated, but basically what we do is we do some math magic and we transform the data to a sampling distribution. And we can think about this distribution curve like a normal distribution where there is a peak, and it is like a symmetric hill, a symmetric bell curve. And we can think of this distribution curve as the likelihood of our hypotheses, where the x-axis is going to be different t values, t statistic values, right? And then the y-axis is going to be the likelihood, like the frequency likelihood values of seeing a particular t statistic in the data. And this sampling distribution, yeah, I said that already. It's shaped like a bell curve. I had that in my bullet points twice. I guess I just really wanted to emphasize it's a bell curve. So on the x-axis, on this figure here that's pulled from the hypothesis testing paper that I cited, on the x-axis of this sampling distribution are a few important values to note. So one of these values is called theta critical. This is the value in the t value, I guess. That's the cutoff for either accepting or rejecting the null hypothesis. And how we determine this theta value is that it's the point at which the area under the curve from this theta value to the end of the curve is equal to alpha. So in other words, this red area here, and I'm sorry for those listening, this is probably very confusing, but basically like the tail of the curve, the area that becomes equal to 0.05 is defined by this theta critical value to the end of the tail of the curve. So it's sort of like the last corner, I guess, of the curve before it goes down to 0. So that's how we define this critical theta value, is making the area under the curve up until that point, or rather past that point, 0.05. And then we have this t statistic that we created before we looked at the sampling distribution, right? The t-statistic from the data set that was based off of the sample means and the variances and the sample sizes, right? So this t-statistic will lie somewhere along the x-axis. And we can find where along the x-axis this t-statistic value is, and then find the corresponding point on the curve where the t-statistic is, and then do some math to figure out the area under the curve from the t-statistic value to the end of the curve. And that value is called our p-value. The p-value is the probability that our results in our data are observed by chance. So in other words, the false positive, the observed false positive, where it's like, this is actually just an accident. This isn't really a difference. It's an accident. So if the p-value is less than the alpha value, which again, alpha is usually 0.05 or 5%. So if there's less area under the curve from the t-statistic to the end of the tail compared to the theta critical value to the end of the tail, in that case, there's less p and more a, more alpha. Then in that case, we can reject the null hypothesis, right? Because the p-value is lower than 0.05, the alpha value. So this means we can reject the idea that there's no difference between our groups, and instead we can accept the alternative hypothesis that there is a difference between our groups. If the p-value isn't less than alpha, so if it's greater than alpha, meaning that there's more area under the curve from our t-statistic to the end than there is from the theta critical statistic to the end, then we cannot reject the null hypothesis. So we can't say with certainty that there is a difference between the groups. We have to say the groups are the same. We don't see a difference because our data are not significant enough to draw that conclusion without the higher risk of a false positive. So in other words, if the p-value is greater than 0.05, which is the alpha value, then it's more possible that the null hypothesis is correct. So we can't reject it. You guys definitely hate statistics now. I know it. But you know what? You're in good company because so do I. Just kidding. I like statistics sometimes. When I get it, I like it. When I don't get it, I hate it. All right. I think, I forgot there were bullets on this. So from this, we get the p-value, and there it is in words. If p is less than alpha, we can reject the null hypothesis. If p is greater than or equal to alpha, we cannot reject the null hypothesis. The methods that I talked about here require a lot of math, right? If you're looking on the screen, you see an integral sign, you see infinity signs, you're like, what the hell is going on here? Baby, I don't know either. But you know what the good news is? That Excel knows. Microsoft Excel knows exactly what's going on here. So all you got to do is go over to Excel and plug in all of your data points and then tell Excel to do a t-test. And it does all of this for you. And then it does all of this for you and it gives you a p-value. And then with that p-value, you can say, is this greater or less than alpha? And then you decide whether you can decide, I just had a brain fart. You can decide whether p is less than alpha, and you can reject the null hypothesis, or if p is greater than or equal to alpha, and then you can not reject the null hypothesis. So Excel does all the hard work for you, and then you get the glory of saying yes or no. So Excel and like other stats software can help you conclude whether there's a real difference in your data or not. All right, let's go to my example of a t-test. My question that I made up off the top of my head is there a height difference between New Yorkers and people in California, Californians? This was a very stupid question, but I was like, I just need a low-hanging fruit, and I was just in California, and I live in New York, so this is what you're getting. Here are my hypotheses. My null hypothesis is that the height of New Yorkers is equal to the height of Californians. my alternative hypothesis, which is actually like where the interesting thing is I think that the height of New Yorkers is not the same as the height of Californians. Okay? So next step, after I have my hypothesis, is to collect the data. So I asked 10 Californians and 10 New Yorkers their height, and I put the histograms here for Californians and New Yorkers. The average height in inches of the New Yorkers that I asked 10 New Yorkers. The average height was 72.7 inches with a standard deviation of 2.3 inches. The average height of the Californians that I asked was 68.2 inches with a standard deviation of 3 inches. So you can see, based on these clunky little histograms that I made in Excel, is that for the Californians, they had a slightly higher standard deviation. So their histogram is a little more spread out, right? Whereas the New Yorkers had a little bit smaller standard deviation, so their peak is a little more compact. It's tall and skinny, versus the Californians, which are a little more spread out. Okay, so that's the data that I collected. Now I run a t-test in Excel. Based on the hypotheses that I had, my null and alternative hypothesis, and the data that I collected. And I get a p-value of 0.0014. This p-value is less than the alpha value of 0.005, which means that I can reject the null hypothesis, and I can conclude that New Yorkers are not the same height as Californians. That's the conclusion that I make. The heights of Californians and New Yorkers are not the same, based on the data that I made up. Isn't that quick and easy? And I spent like freaking 20 minutes explaining it, but it's like, oh, just kidding. Excel can do it all. But remember what I said before at the very beginning of the episode? Beware of the bias. What if every single New Yorker that I asked played on the New York Knicks? Or most of the New Yorkers that I asked were on the New York Knicks. Then this is a biased sample, right? So what I can do is increase my sample size to correct for this sampling bias. So if we increase the sample size to 35 people per group, per state, then we're getting a better representation of the full population. Granted, it's 35 people, so maybe not that much better of a representation, but better than 10, right? Now these are our new data and our new distributions, and we can see that the average New Yorker height in inches is 70.1 with a standard deviation of 2.77. And then the average height of a Californian in inches is 70.0 with a standard deviation of 2.95. So now the averages look a lot closer together now that I've added this new data in, and I've asked 25 more people what their heights are. When I run a t-test on this data, I get a p-value of 0.0807. In this case, p is greater than alpha, so 0.08 is greater than 0.05. So in this case, we can't reject the null hypothesis. So from this conclusion, we have to say there is no difference between New Yorkers and Californians in height. But in spirit, we're better. Just kidding. Am I? Okay. I wanted to talk about a few more stats concepts, but I've already been talking for like an hour, and I'm pretty sure nobody cares anymore. But one thing that I want to talk about that I alluded to in a previous episode was about statistical power. There's this thing called a power analysis, where we can see how big or small of an effect you can detect with a certain sample size. So this sort of alludes to, again, the idea that like, oh, a larger sample size, a better representation of the population, but it can also help us find smaller effect sizes, meaning like smaller differences in the means if we have more people to survey, to measure, etc. And also with a power analysis, we can determine how big our sample size needs to be in order to see significant effects in our data. So like it's helpful before we start collecting data or we start planning our experiments even. Power analyses are helpful for that also. But then there's also key concepts like degrees of freedom and multiple comparisons corrections that I thought I would talk about, but we'll save that for a rainy day, okay? All right, let's get to the closing messages for today's episode. The first closing message is, are you still awake? Are you good? Wake up. Okay. No, but actually, I hope this episode provided some sort of understanding to statistics, and I hope it did it in like a friendly way, because I know, trust me, I know statistics sucks, but I hope that my outline of statistics was a friendly way to remind you of the importance of math and statistics and why they're so important in science and data analysis, and also in interpreting that data analysis and interpreting our results to draw conclusions. And hopefully in a future episode when I say the p-value was, 0.001 in a study summary, you'll be like, oh my God, that's significant data. That's some significant data. And I'll say, you're right. That is significant. All right, that's all for this week. I'm sorry that I missed a couple of weeks, but I'm very happy to be back, and I hope that I will be much more consistent with my weekly episodes now. But yeah, thanks for holding out and waiting for me, and I appreciate your patience. Yeah, now I'll do the usual spiel. Please don't forget to follow, rate, and review the podcast wherever you're listening. You can subscribe on YouTube now as well, so please do that. Please. You can also follow the show on Twitter and Instagram. Both of those are at samsplainingsci. Connect with me there and ask questions if you'd like. You can also submit your questions on samsplainingscience.com/ask. So if you have anything that you want Sam explained to you, ask away. Thank you so much for listening to this week's episode. I hope you learned a little bit and laughed a little bit, and I will talk to you next time. Bye.